Imagine a world powered by a never-ending source of energy, like a magical wellspring just beneath the surface of reality. This isn't just a fantasy, it's a tantalizing possibility that scientists are exploring. That's the exciting idea behind zero-point energy, a concept from the world of quantum mechanics. It suggests that even in a vacuum, where we think there's nothing, there's actually a seething sea of energy. This energy, also called vacuum energy, is the lowest possible energy a system can have, even at absolute zero temperature. It's a fundamental aspect of quantum fields. It's a captivating thought. Could this solve our energy problems? Imagine harnessing this energy to power everything from our homes to entire cities. Could we power our homes and cities with the quantum vacuum's hum? The potential is enormous, but so are the challenges. But there's a big hurdle, the laws of thermodynamics, specifically the second law. This law states that energy systems tend to move towards disorder, making it difficult to extract usable energy from the vacuum. Understanding this law is key to unlocking the mystery of zero-point energy. Scientists are working tirelessly to see if we can overcome these barriers and tap into this incredible energy source. The second law of thermodynamics is like the universe's careful accountant, meticulously keeping track of all energy transactions and ensuring that nothing is ever lost or gained without a trace. Simply put, it states that whenever energy changes form, some of it inevitably gets lost as unusable heat, which in turn increases the disorder or entropy of the system. This is a fundamental principle that governs all natural processes. Think of a hot cuppa left on the table. Over time, the heat from the tea will naturally flow into the cooler surrounding air. The heat will continue to disperse until the tea and the air around it reach the same temperature, demonstrating the natural tendency towards equilibrium. This process can't be reversed unless you add more energy to the system, like reheating your tea in a microwave, which requires an external energy source. This law has significant implications for the concept of perpetual motion. It essentially tells us that creating a machine that can run forever without any energy input is impossible. No matter how efficient a machine is, it will always lose some energy in the form of heat. And this lost energy contributes to the overall increase in entropy. Every machine, no matter how well designed, will lose some energy and create more entropy, underscoring the inescapable nature of the second law of thermodynamics. At first glance, zero-point energy seems to break the second law of thermodynamics. If the vacuum is full of energy, can't we use it to power our world, ignoring entropy? This idea sounds like a dream come true. However, this is where the crucial difference between energy and usable energy comes into play. Not all energy can be harnessed efficiently. While zero-point energy is indeed a massive store of energy, it's constantly fluctuating in unpredictable ways. These fluctuations are random and chaotic, making it extremely difficult to extract any usable work from them. Imagine trying to power a windmill with thousands of tiny fans blowing in random directions. It would be nearly impossible to get consistent energy. The energy is present, but it's not in a form that we can use effectively. This explains why zero-point energy doesn't actually break the second law of thermodynamics. It's like having 1,000 monkeys randomly typing on typewriters. There's a lot of activity, but not much meaningful output. The energy is there, but harnessing it in a useful way remains a significant challenge. The McGinty equation helps explain zero-point energy and thermodynamics. This equation, named after its creator Chris McGinty, gives a theoretical framework for how zero-point energy works. While still being researched and debated, it offers a compelling model for how zero-point energy interacts with spacetime. The equation uses ideas from quantum field theory, fractal geometry, and gravity to describe how energy fluctuations in the quantum vacuum are affected by the shape of spacetime and the presence of matter. It suggests that zero-point energy is everywhere, but accessing it isn't the same throughout the universe. Navigating the quantum sea. How the McGinty equation upholds thermodynamics. The McGinty equation doesn't contradict the second law. Instead, it shows us how zero-point energy works this law. The equation suggests that even though the quantum vacuum is full of energy, getting to it means navigating tricky quantum fluctuations. These fluctuations, affected by gravity and the fractal geometry of spacetime, make extracting usable energy complex and possibly inefficient. The McGinty equation implies that trying to take energy from the quantum vacuum would create entropy somewhere else, keeping the second law balanced. Energy whispers, fluctuations, geometry, and the pull of gravity. To understand the McGinty equation, we need to look at its parts. Quantum fluctuations are the inherent uncertainty and jitteriness of energy levels in the quantum world. These fluctuations, seemingly random, are affected by the curve of spacetime, as Einstein's theory of relativity explains. Fractal geometry, a mathematical concept describing infinitely complex patterns, is used in the McGinty equation to model the intricate structure of spacetime at the quantum level. This fractal nature, along with gravity, dictates how energy fluctuates in the quantum vacuum. The price of power. Why energy conversion always comes at a cost. The McGinty equation highlights something important about zero-point energy. Converting energy has a cost. Even if we could tap into the quantum vacuum, turning that energy into a usable form would create entropy. This is because trying to extract energy from the vacuum means interacting with its fluctuating fields. This interaction creates order in the system, which, according to the second law, must be balanced by more disorder elsewhere. We'd be borrowing order from the universe, and we'd have to pay it back with entropy. From theory to reality, practical applications and the limits of zero-point energy. While harnessing zero-point energy is exciting, the McGinty equation suggests practical uses might be limited because it's hard to extract usable energy from the quantum vacuum, but research continues to explore ways to use this vast energy store. Some scientists think that by changing the local shape of spacetime or using specific frequencies within the quantum vacuum, we might improve energy extraction. However, overcoming the second law remains a huge challenge. The harmony of the cosmos, zero-point energy and the enduring laws of physics. Zero-point energy, while fascinating, doesn't break the laws of physics. The McGinty equation, though still being developed, helps us understand how this energy interacts with space-time. While the dream of limitless clean energy from the quantum vacuum remains a challenge, exploring zero-point energy gives us amazing insights into the universe and its laws. Our quest to understand zero-point energy shows our curiosity and desire to unravel the cosmos's mysteries.